Welcome back, welcome back, welcome back. I'm Miss Lisa, and this is my YouTube channel, all things math and science that I want to talk about. Today we're talking about physics, and I want you to like, share, subscribe. I have a goal to get 1,000 subscribers so that I don't have to record and upload with it taking up all the memory on my phone. Instead, I could just upload the way I used to last year on Facebook Live. But YouTube's better because Facebook gets rid of your videos after a while, and YouTube doesn't. As you can tell, there are videos on YouTube that have been there for a long time. So that's why I switched, but it's a little bit of a pain. So share it with all your homeschool groups. Tell them about it. Free math and science on YouTube. So I'd love for you to share it and to bless more homeschoolers. So as you can tell by what I've said so far, these classes are primarily designed for homeschoolers. But if you like the way that I explain this, come on in. We're going to talk about momentum and its conservation of momentum. Now, when I do these videos in physics, there's always two, because there's one where I talk through the concepts, and the second one I do the math up close and personal with the camera right on my calculator and on the problem. So be sure to come back and watch the math one too, because I think the math is interesting. I think like sometimes it's fancy math, like some of the ones we'll be doing this time involve trig. And that's fun because it's different. You do the same old math for years and years, and finally, something different. Sine, cosine, and tangent. So that's fun. So that's what we'll be talking about. We'll talk about the ideas first in this one, and then the second one will be the math one. It's the same with my Algebra 1 and Algebra 2 classes I have on here. They have where I talk through the math concepts and do them on the board, actually. And then I do calculator labs where I'm right up on your calculator teaching you how to use your TI-84 calculator. And that's the one I use in these physics too, and which leads me to something I need to remember to say in the next video too, is when we talked about vectors before, and we're going to be talking about things that can be added by vectors in this one, there's a great app. It's called SciTools, SciTools, and it has in it a vector addition thing where you end up where it will do your physics problems for you. And last year, my kids in my physics class did it, or was it the year before? But anyway, they worked through all the math and really struggled, and then I showed them SciTools, and they were like, this is so easy. It's a little bit not intuitive about how to use that program. I know I made a video for it on Facebook last year. If, I might make another video for it, but I might not. I might just let you figure it out because it's not that hard, and or look for other videos for it. But it's an app for the TI-84 called SciTools, and it's very helpful with these trig problems. But not all the problems on this one are trig problems. A lot of these were just setting up knowns and unknowns and solving for the one we don't know. All right, so let's talk about all that's to talk about what we're going to talk about. Let's talk about it. Momentum. So momentum is so this is chapter 9 in your book, if you're going along with the book. Momentum is one of the many things that is conserved. You know how we've learned about the law of conservation of mass, the law of conservation of energy, and when things are conserved, it means the total of it before and after whatever happens, if it was chemistry, we call it a reaction or whatever happens, that the input equals the output. So we see this throughout nature, and I always tell all of my students I teach in public and homeschool that nature likes balance. So there's always this balance in nature, and nature is always going to go for the balanced approach. And so we see that in balancing chemical equations, we see it in energy, in atoms, and we see it all the way into these laws of conservation. So what we're going to talk about right now is momentum. So you already know about momentum. You've been living your life, and experiments happening around you, whether you realize it or not, and you've been learning whether you realize it or not. So let's imagine, and you're going to realize you already know the answer. Let's imagine that there are two people barreling down at you with a big force. They're going very, very fast. They're not going to be able to stop. And you have to choose which one's going to hit you. And one is an Atlanta Falcons football player, a huge man with big pads and muscles and mass. And the other one is a 3-year-old. And it is a 3-year-old little boy who is, you know, very determined to run you down. If you had to pick one of them to run into you and smack you, you'd pick the little kid, wouldn't you? And why? It's momentum. And the little kid might even get stopped. The football player, once he's going, he's gonna take you out. So momentum is the mass times the speed. And what do you think the symbol for it would be? Maybe an M, maybe an M-O. Nope, it's a P. It's P. And, my son Nathan said that he had a professor who said there must have been a big fight over which things got which symbols, and momentum lost because it's a P. Excuse me. In the fall, I always have allergies. I know it's a pain, but I also don't like to take anything for it. It doesn't really bother me, but it makes my voice sound just lovely, I know. All right, so momentum is a P, and it equals mass times velocity. So there's our formula. Now, sometimes you hear impulse, and impulse is the change in momentum. Remember that triangle is the Greek letter delta, and it means change or difference. So momentum is P, delta P is impulse. So, and you already know about these things. You have been living your life and you realize that mass and speed together makes something. And sometimes people don't really give momentum enough respect. For example, people who stop on railroad tracks, and they're stopped on a railroad track and here comes a train. That train is not going to be able to stop for you. It has too much momentum. So don't stop on the railroad tracks. Stop before, stop after, don't stop on it. But every year you see somebody or they'll try to go in front of the train. Like they'll go around the guards, or they'll try to zip over and beat the train. And you see it every year on the news. This truck, pickup truck, getting hit by the train. People who hear it on the news. Somebody died because they tried to beat the train. The train cannot stop. It's got too much momentum. And you could even see that with like a big truck on the highway. People will cut in front of a big truck, and the truck cannot, and if you cut in front of it and you're going just a little bit slower than that truck cannot get slowed down fast enough. They've got too much momentum. But if it's a little car, then they could slam on their brakes and it'd be okay. But momentum, mass and speed make momentum. So I've been talking about mass. It could be speed. It could be something just going too fast. Maybe it's not all that big, but it's going too fast that it cannot stop. A bullet's a good thing like that. Bullets are not big, but they've got lots of speed, and that gives them a lot of momentum still. And bullets can't stop on a dime. You know, that it's, well, I guess if they shoot you, they can. They hit your bone. They also stop with water. If you ever see it, it's a real interesting Mythbusters where they show that if somebody's underwater, bullets really can't get to them. They shatter. When the bullets shatter when they get to the water. So that's interesting too. Water is just an amazing chemical. We wouldn't have life on this planet without it. All right. Okay. So we'll be doing all the math in the next video. So we're going to learn how to calculate momentum. It's pretty easy. Impulse is the change in momentum. So we'll be doing some problems with that too. Angular momentum is momentum in a circle. And where you've seen this is the Olympics. The ice skaters, they'll be spinning with a leg out, and they spin kind of slow, and then they pull that leg in and they speed up, and it is conservation of angular momentum. Angular momentum is something moving in a circle. It's the momentum it has instead of linear. the angular momentum is constant. So what we're thinking about is torque. And remember I taught you torque last time. Torque's my jaw, as my daddy would say. It is, remember, torque comes from the force times the length of the lever arm or lever arm if you're up north or out west or anywhere but the south, I think. So that lever arm is changing as the ice skater pulls their leg in. It's getting shorter, so that's why they go faster. And then they'll do their arms up to make themselves really skinny, and they go really, really fast, and then they spread their arms out and they go slower again. Now, you might not be an amazing figure Olympic ice skater who can do that, but I bet you've done your own experiment with this. Can you think of when? Okay, it's when you discovered a chair that would spin all the way around. And you sat there and you would go spinning in it, and you'd stick your legs out and you would go slower, and you'd stick your legs in and you'd go faster. If you haven't done it, if you've gotten to this point in your life and you've never done that, go find a spinny chair and do it. Get someone to get you spinning. Or they used to have in playgrounds what we called merry-go-rounds. They were a spinning metal disc with little things you can hold on to. And you could... people would spin you around on those, and you can stand right in the middle, and then with it going, and then you could you could sometimes feel some different things with angular momentum with it. I thought of another one. Oh, swing set. You remember when you sat on the swing and you got tired of going back and forth, and instead you spun the chain up, and then you let it go, so you would sit there and spin. And if you put your legs out, you went slower. But if you pulled your legs in, you went faster. Do you remember that? If not, go to a park, because they've gotten rid of a lot of what my kids called the unsafe playground equipment, which they thought was great. We would search out unsafe playgrounds when my kids were little. I don't know what that says about me as a mom, but I played on them as a kid and survived, so I thought they could too. So there used to be what we called an unsafe playground in Hiram, Georgia, near here. But then they went in, and it had the teeter-totter, the seesaw, and it had that little merry-go-round thing, and high slides with no thing to keep you from falling off of them that went real fast. And those were really fun. It's what I had when I was a kid back in the 70s, the dark ages. But there was one left in Hiram when my kids were little. We would drive all the way to Hiram, Georgia. We don't live there, but we'd drive there to play on the unsafe playground. And then, of course, they went in and updated it, and they gave it all the new modern safe playground equipments. No more teeter-totters, no more seesaws, no more of those merry-go-round things, because you could just fly off of them. They were so fun. And no more super high slides, and now they're short and they're plastic and they're covered and not nearly as fun. Now you got to go to whitewater and go down the water slide to go down the big ones. So, and that's fun too, and a little unsafe. I've come off those before going, oh, that kind of hurt. But then I go again. So what does that say about me? All right. So angular momentum, you already kind of know about it, read about it. The next thing is talking about the conservation of momentum. One of the places we see this is through Newton's third law. Do you remember what it is? For every action, there's an equal and opposite reaction. So where we see this is that this change in momentum is conserved, and that momentum is conserved, and that's what the momentum you put in is the momentum you get out, and that's why it explains the Newton balls. So you've seen those little office toys that have the little balls on it. I have one on my desk at school. If I hadn't have taken it to school, I'd show it to you now. But it's on YouTube. I'm sure you can see it. And I'll even tell you the one to go see. But anyway, it's like a bunch of little balls on these strings. And you take out one and you pull it and it goes click, and one ball comes out the other side. One. You pull back two balls. See, we're using conservation here. And you let them go click, and what comes out? Two balls. Click. You do three balls, where there's three on this side and only two on this side. You let them go, and three balls click out, click, and then you do it with four, and they'll go click, 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 leaving behind the one. So you see the math that momentum is conserved. Now, if you don't have one of those things, and I can't show you mine because it's off at school, but there's a video, and it's a great one. I know it's out there, you can find it, but it's where this person made this Newton ball thing with bowling balls. So they go click, 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 and then they also they do all this stuff with it. They get waves going and resonance, all these other things we've talked about. So somebody set this up in their backyard with all these bowling balls, and it's really cool, and you can go watch it. I'm sure you can find the Newton bowling ball experiment, and you'll find some good videos. Just always remember, go with your mom if you go on the internet. One time we were doing a homeschool thing, and we went to something like, the London Museum. It was a legitimate website, and downloaded a picture of Catherine the Great wearing a peasant outfit. Once we got the picture on our computer and opened it up, it was not Catherine the Great, and she was not wearing a peasant outfit. In fact, she wasn't wearing anything. So always go with your mom. Let your mom open files first and look first, and then if it's okay, then you can go. But don't go. It's a jungle out there. Don't go exploring without your mama. Take your mama on the exploration. All right. We learned our lesson about Catherine the Great. And one time it was something with Winnie the Pooh. We were downloaded some picture of Winnie the Pooh, and when we clicked on it, it was not Winnie the Pooh. It wasn't even poop. It was something completely different. All right. So that's momentum. You're going to see the math. Now your lab for this one, it talks, they have some cars, and they run them into each other. Cars that are springy cars. I have some. They're called physics cars, and they are crazy expensive for what they are. This little plastic car with a spring on it. You could probably make one with some car you've got, sticking the spring on the end. But the other thing is there's some really cool momentum things you can do other than that. And we did one of these last year with our physics class. We did one, there's two different ways, and the first way is the better way. So let me tell you, this is one thing you do. You take a basketball and a tennis ball, and you hold them together and you drop them together. So when they drop, the basketball hits first and starts bouncing back up. It takes all of its momentum and it transfers it to the tennis ball, and the tennis ball just rockets far away, and the basketball falls back down to the ground. Thud, thud, thud. So that one's really fun. Go do it. Go find a big ball and a little ball. It doesn't have to be a basketball and a tennis ball. Use what you got and go try that. It is so fun to make the tennis ball go rocketing off by transfer of momentum. Another one that there is this thing called the American Chemical Society that's like a society of all the chemists, and that I used to belong to. And then there's one called the American Physics Society. And they send out free little labs to physics teachers. And it was to show this. And what it was is you took a super ball and you shoved a straightened out paper clip on it, and you put a straw on it, and you drop it, and then the super ball hits the ground. It transfers its momentum to the straw and shoots it off. It didn't work. The problem is it didn't fall straight enough. That weight of the paper clip and the straw would make it turn, and then it didn't work. So it was very disappointing. We got the kit from the American Physics Society. We got the ball. In my brain, this is going to work because I understand how momentum works. It didn't work. In fact, all the experiments they sent me last year, none of them worked. They were all disappointing. They were cool things, and I took all the equipment, and I thought, I can probably make experiments that really do work out of these, but none of them. They were like probably 10 to 20 experiments. None of them worked. And I'm like, why did they waste their money sending these free kits out to people of experiments that no one bothered to try and see if they worked? A lot of them were versions of other experiments I had done through the years that do work, like the tennis ball basketball experiment. It works. They had one that was a friction one that I had done before with wood and sandpaper and our tabletops, our lab tabletops, and it worked great. They did it with sandpaper and clay, and it just did not work. So it's like they needed to have paid somebody to try them first with actual students, not physicists. Maybe it was because they have PhDs, they did it right, and they needed some non-PhDs to do it. All right, so the law of conservation of momentum is the momentum of any closed, isolated system does not change. Now, what does that mean, closed, isolated? Okay, so you have to define what's in the system. For example, in your book, it's got, in a few pages, it's got some girls on roller skates. And if you look at the two girls as a system, and one girl pushes the other one on the roller skates, one will go forward and one will go backwards, because for every action there's an equal and opposite reaction, and momentum is conserved. But if you define the system as just one of those girls, she's there all by herself, and suddenly an outside force comes and pushes her, then it would look like momentum was not conserved because she was still, and then she's going. But it's because you have to look, you have to be real careful and make sure you don't have other forces, other things going on that you didn't mean. Like the physics people with that little ball experiment. They looked at, well, this should work. But the reason why the tennis ball, basketball works is because you have it in your hands until you let go of it. So it has, you're making the orientation stay right. With that the little thing they did, you're not holding the whole thing for, as it's getting closer to the ground, and it has those extra forces as it makes it turn. It's like why your toast always lands on the butter jelly side down. It's just, things turn to the heavy side down a lot of times because of, and we know that things fall all at the same rate. It has to do with the resistance. So it's a pain. It's a pain. All right, that didn't work. But just think of all the time I'm saving you, not making you do that experiment. All right, so there's a formula, and it's basically that the momentums, if you have two things, that the momentums before the event happens equals the events, the momentums after it happens. And so they've got train cars. They've got one train car, and here comes another one. This one's still, this one's moving fast. They click together, so it is a kind of collision where they're not bouncing off. They're train cars that have those couplers. They couple together, they become one thing, and they'll move off together at half the speed the original train car had, because it gave half of its energy to the still train car. They move off together at half the speed. Momentum is conserved, okay? And you've probably, this is all just intuitive. It's all common sense. I've had kids say before, Miss Blackburn, physics is just playing with toys, because I get out the balls and the cars and all that. Physics is just playing with cars, common sense, and math. And that's the truth. That's what physics is. All right, so we're going to do a problem with that. Internal and external forces. I already told you about that. The external force of the girl on the roller skates. And then the last thing is conservation of momentum in 2 dimensions. So this is like you have a ball coming in and it hits a ball, like not straight on where they go together, but at an angle where they go off at angles. So when we get these 2 angles, we're looking at vectors again. So we're going to use Pythagorean theorem or trig, just like we did before, but this time we're applying it to momentum. So I think momentum's really fun. I like the Newton ball little lab things, and the labs you do with the little hands-on stuff. So and remember I told y'all in the margins you have little blue things that are pocket labs. A lot of those are fun and easy to do with what you've got. And so have fun with this. Come back and watch the second half with the math. Read your chapter. Do the practice problems. Remember, I give you the problems that the answers are in the back. So don't just copy the answers. That's not going to help you. Try the problem and then go look at the answers. Don't do all the problems and look at all the answers. One problem, go look at the answer. If you did it wrong, fix it. Try the next one. Go look at the answer. And maybe by this time you've learned how to do it and you get it right. Don't practice a whole page of math wrong, putting it in your head that that's the way you do it. You always want to do a problem, check it, do a problem, check it. So that's the reason why in my algebra classes and my math classes I teach too, I always give you the problems to do where the answers are in the back of the book. Could you sit there and copy all the answers? Sure, but you're not going to learn and you're going to fail the test. The point of homework is to learn so that you can pass the test. The test is when you're tested. Homework is when you learn and when you practice. Like for sports, how you practice for a sporting event, you have to practice with math. All right? So, like, share, subscribe. I'm Miss Lisa. Science is great.